Chemistry time. Hopefully it's on. Is it picking up? Okay, it is picking up. That'll be a nice part of the video when I just tap that thing. Okay, we're talking about science as a topic today. So let's put... Well, I'm having a bit of trouble with my wire. There we go. That seems good. That seems good. Okay, our objective is something like describe the importance of chemistry in society. Describe the importance of chemistry in society. Describe the importance of chemistry in society. Your book begins with this, I think, pretty nice little, that's called A Tale of Two Substances, a pretty nice little intro to the importance of chemistry. And the two substances it talks about, are oxygen gas and ozone. Do you remember this from your reading? So we have oxygen gas and ozone. What, for those of you who read, was the main difference between those? What is the difference between those? No, hydrogen's not involved at all. I'm going to change the view here. Someone else? What is the difference between them? The only difference is their formula. What's the formula of oxygen gas? O2, and the ozone gas is? O3. It's O3, thank you. It's O3. So are they made of the same element? Yes. Are they the same substance? No. They're different substances. Your book defines substance then, and it says that a substance is any pure matter with a set composition. Pure matter with a determinate, let's put that, determinate composition, meaning that we can determine what it is based on its composition. And it talks about the ozone layer. Okay, now listen. There's this is what when I was a little kid, one of my, I think my first or second grade teacher said that there's an ozone layer. She did a fairly poor job of explaining what that was, and she said there's a hole in it. Uh-oh. She's right. She was right at the time. She's less right now. We'll talk about that. But there's a hole in it. And that was because we were talking about, like, pollution and stuff we were talking about. And I was here in Nebraska, and I thought, like I said, she did a terrible job of explaining this. And so I thought she meant, like, this morning there was a hole in the ozone layer, which is around the planet. I thought this is what kept the atmosphere in. So I thought, like, all day long, I was like, oh, the atmosphere is just going to, like, leak out the planet, and we're all going to suffocate. And everyone was just, like, having recess and doing math, and I was like, the world is ending, guys. She said there's a hole in the atmosphere, and we're all going to die. Like, I really thought this was true for a long time. A long time. I was like, I thought this was a much bigger problem than it was. Don't be like me. And that's not the case at all. It's certainly not a containment layer around planet Earth. It's not even really a layer as such. What it is, wrong. I really thought, like, and it was windy that day. I was like, oh, that's all the air flowing to the hole that's going to make it so we all suffocate. So I was really worried about that. And I even went as far as to think, I thought in my little first or second grade brain, I thought, maybe everyone else is suffocating and they just are like, they're just being brave about it, and I just like maybe they're all suffering inside like I am, and that no one's just talking about it. We're all pretending to be okay. Then we didn't die, at least not most of us then. What it really is the whole planet. This is going to be a very similar around the whole planet. This is not what it looks like either. But the whole planet has, the atmosphere itself is this layer, right? So far, so good. This is one of the dumpiest drawings you've ever seen in your life. But what happens is as the sunlight comes and strikes the atmosphere, a reaction occurs. So the whole atmosphere has a similar composition on a chemical level, except that this reaction, the sunlight, and specifically a part of the sunlight called the ultraviolet light, comes into the atmosphere and it causes this reaction to occur. Whoops. Oxygen gas becomes ozone gas in the presence of ultraviolet light. And two things happen here. Obviously, this ozone is made. That's the first thing. But also, the ultraviolet light is absorbed by this happening. So there's another less gross, but still real misconception that people have about this. People think that there's this blanket of ozone that the fact that it exists protects the planet from the sun's light somehow. And that is a much more common misconception than an idiot thinking that they were going to suffocate to death. But it's still a misconception. It's wrong. That's not really what's happening. There's not like a single layer of ozone that's like acting like a shield, making everyone happy. What does happen is that at this specific layer of the stratosphere, it just so happens to be at this layer, this reaction occurs. At that layer, there's a high enough concentration of oxygen that this commonly occurs, that this turns into this. It's not the presence of this that protects planet Earth. It's this reaction, the whole dang thing, the whole chemical reaction. This reaction protects planet Earth because the ultraviolet light is absorbed. What's left over then is the ozone, which really, I mean, almost coincidentally, or coincidentally certainly, but almost poetically, the ozone itself is poisonous. Ozone here on the surface is used to sterilize things. Like one way of sterilizing pools is that they bubble ozone through the pool to kill all the bacteria that are in it. They use ozone for a lot of, antibacterial, not just antibacterial, but antibiotic properties. It'll kill any life.
So if you're in the pool and that happens, you're dead?
No, probably not. So even though the ozone is poisonous, this reaction stops the ultraviolet. I mean, let's not even say that. It doesn't really stop the ultraviolet light. This reaction is through the absorption of this to make this. And so that reduces the amount of ultraviolet light getting through, and especially at certain dangerous frequencies. Is this balanced, this chemical reaction? No? How do we balance this so that it is balanced? No, you can't do that. How do we balance this so that they are the same on both sides? You should remember this from physical science. You can't do that either. What can we change when we're balancing? Yes.
The oxygen by 3 and then the ozone by 2.
Very good. Very good. So now it is balanced. There are 6 oxygen atoms on this side and 6 oxygen atoms on this side. The other thing we want to talk about, and that's one key principle of chemistry that we talk about that you already know. Another key principle of chemistry that we talk about that you already know, and that we have talked about already in this even, is that these two, are they the same? They're both made only of oxygen. Are they the same? No. These are separate substances. Separate substances with totally different properties. The other classic example is this. What's this? Does anyone know? You should remember, probably. NaCl. Sodium chloride. What is it? Yeah, but what is it? Yeah, what is it, though? You know this by a much more common name. Sodium chloride. Salt. It's table salt. Remind yourself that this is table salt. You have experienced table salt before, yeah? Sodium is a explosive metal, just sodium. It's a metal, looks just like that nickel that Peyton is very proud of, except it's super soft. You can cut it with a knife, and also if it touches water, it will explode. And then chlorine is a green, poisonous gas. So even though this is made of sodium and chlorine, does it have similar properties to these at all? No, it's completely different properties. Substances have a determinate composition, but they also have completely different properties from their constituent elements. Meaning that the things that make them up have completely separate properties from the thing that is made. And so those are two, I don't know, kind of example core principles of chemistry that we're going to talk about throughout this year that you already know or should already know.
What does that say? Completely different properties
From their constituent elements. Here's another thing that comes up very, very often. We need to talk about real quick the difference between mass, you still see this? Yep, mass and weight.
weight is how much something weighs on Earth, and also
You can't use weight. Yeah, okay. So it's the gravitational force within a given gravitational field. So in the gravitational field of Earth, your weight is the force of Earth's gravity on you. In your gravitational field, Earth's weight is the force of your gravity on Earth, which is by definition the same as the other one. What I mean by that is that here's you on planet Earth. Earth pulls down on you, we'll just use pounds because you're used to it, 110 pounds. But you also pull up on Earth 110 pounds because of Newton's third law. Why don't you notice that second one? Yeah, because the Earth is so much more massive that it doesn't have the acceleration that you would when you fall or whatever as this force is affected. So the weight is the gravitational force within a certain or within a given gravitational field. What is mass? This is much more basic. More basic, let's put that down. More basic. Things have weight because they have mass. That's what I mean by more basic. More basic, comma, what? What else? Yep, it's a measure of the amount of matter in an object. Will you always weigh 110? We always weigh, emphasis on the weigh. Will you always weigh 110 pounds everywhere in the universe? No, because it depends on the gravitational field you're in. Will you always have the same amount of mass? Yes, you will always have the same amount because that's the amount of matter. That is, at a given moment in time, you'd always have the same amount of mass, right? If you clip your fingernails, your mass changes. But when I mean like at a certain snapshot, your amount of matter would be the same no matter where you were. Like if you were teleported into the Triangulum galaxy, it doesn't even matter where, you would still have the same amount of mass because it doesn't depend on the gravitational field. This is more basic, one, because this depends on it, but also because this has fewer conditions. This changes depending on two variables, mass and gravitational field. This only changes with the change in amount of matter.
what is the word after within it?
Given.
Given?
Nope, given. Okay, the remainder of your chapter is review. You should already know all of the rest of it, starting with lesson 3 and on. This was all review. Well, no, this was review. Some of this was too. But the rest of this is definitely all review, and it's vocab. So if you know the vocab and you remember the rest of it from physical science, you should be good. You have questions? The math you will need to know for this, it looks like you need to be able to find volume from length, width, and height. Can you do that? Let's talk about that real quick here. Capital V equals length times width times height. Capital V is volume, measured in some cubic linear units, meters for instance. Length, or L is length, measured in a linear unit, meters for instance. W is width, measured in a linear units, meters for instance. And H is height, measured in a linear unit, meters for instance. I chose meters because that's the SI base unit for length. When we multiply m times m times m, meters times meters, we get cubic meters, just like in any kind of algebra. Any algebra problem that says x equals m times m will be x equals m cubed, right? You remember that from algebra. Same thing, we multiply the units just like we multiply the numbers. That's the only kind of math you should need. That is definitely review. You've been talking about that in your math classes since you were in elementary school, and certainly we talked about it in physical science. But I think that's the only math you need for this. Other than there's some graphing stuff that you can read up on. Does anyone have questions about the graphing stuff? Does anyone have questions about any of it? There's a whole section here on lab safety, but we already did that, so I'm going to consider that finished. Any questions about any of this? Anything to add?
So, how did, I know they kind of explained it, the star
That shape of a star. This is about the helium video that we watched, and what it was is that the tube is filled with just helium gas, and when it's electrified, they have an electric current running through it. Electricity on one end, electricity on the other end, and as the electrical current runs through the helium gas, the electrons get excited, they move to a higher electron level, and then when they move back, they emit whatever frequency they absorb. So even though you're putting in all frequencies of electromagnetic radiation, they only emit what they absorbed, and since they only absorb the yellow visible light frequencies, they only emit those, so the whole light glows yellow. Other questions?
And then so you know how in the first video we watched with hydrogen, how they blew up that balloon? Can the same thing happen with helium?
It won't explode, it'll pop. Helium is not flammable. It won't combine with anything.
But it will pop.
Yeah, well, it's under pressure, so it'll pop. It's a balloon.
So it won't start on fire.
It won't start on fire because that fire was a chemical reaction between hydrogen and oxygen. Other questions?
That's the combination between hydrogen and oxygen.
Yeah, that is what was happening. Well, it wasn't water, it was hydrogen and oxygen. And then it became water through the process of burning. Other questions specifically regarding chapter 1 of the text? Thank you. Thank you for your questions. Bye.